just loaded up the bins with glue sticks. Is that what you're talking about? Yeah, there's some in there. Probably the one that's labeled glue sticks. I mean, I just got it yesterday after school. Okay, so we're going to open up our little flop, and we're going to do some labeling. Well, it's already labeled, hopefully. So we have two chords. So the chords theorem says if two chords intersect in a circle, then the product of the measures of the segments of the chords are equal. So let's kind of dumb that down a little bit. This is a segment.
I was just reading it.
Okay. Yeah. Because the chords are being divided into segments. So I'm trying to color code it so you can see what's happening here. Do you guys see the 3 different colors or the 4 different colors? I've got green, purple, red, and blue. So it means that NE times EW is equal to KE times EL. Yes, sir. All right. So let's slide over and do an example of that. Is everybody good with that? Am I good to slide over? Okay. So I'm going to try and color code this again. So this whole chord is broken up into red and orange segments. And this whole chord AC, I'm breaking up into blue and purple. So the first chord DB, well, its 2 segments are x minus 1 times 5 has to be equal to x plus 3. Is that a 5 or a 6? Okay, sorry. I'll fix that in a hot second. This is a 6. Okay. Times, where am I? The blue color, times 4. Okay. So I'm going to distribute. I'm looking for a darker color. So 6 times x is 6x. 6 times negative 1 is negative 6 equals 4 times x is 4x. And 4 times 3 is 12. So I'm going to subtract 4x from both sides. But I'm also going to add 6 to both sides. I'm doing that at the same time. Are you guys okay with that? So 6x minus 4x is 2x. 2x equals 18, which means that x equals 9. So let's just go ahead and label our segment. So this segment is actually 12 units long. Let's see, 12 times 4 is 48. This is 9 minus 1, which is 8 units long, and 8 times 6 is also 48. So it works. Do we feel great about that? Okay, let's go to theorem number 2. Theorem number 2 is our secant theorem. If 2 secant segments are drawn to a circle from an exterior point, then the product of the measures of one segment and its external segment is equal to the product of the measures of the other segment and its external. So here's how I want you to think about this. This is the whole thing compared to just the outside. That's what it's saying, the external, right? The whole segment and then the outside piece. Whereas over here, I have the whole segment and its outside piece. So what that means is you can call it ow ow or whoa whoa. I like ow ow. So O times W equals O times W. Outside times the whole equals outside times the whole. That's what that OW stands for. So outside times the whole segment equals the outside piece times the whole segment. So you might hear someone go, ow, ow. Sorry, that's just, okay. Anyway, back on track. So if I wanted to label it by the segments, the outside piece, that's segment SE, multiplied by the length of segment SC, has to be equal to SN, outside, multiplied by the length of segment SA. Ow, ow. Okay. So I'm going to, are we good for me to slide over? So we're doing a little bit of ow, 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 ow. So outside, whole segment, outside, whole segment. So if I work with GL, segment GL, that measure is, the outside is what? Looks like 6, yes? Okay, 6 times the measure of the whole secant, which looks like 6 plus x. Yes or no? Okay. Equals the outside, which is 8, times the whole segment, the whole secant, LS, which is 8 plus 18. It's the whole thing, okay? All right, so let's do some distributing. 6 times 6, 36. 6 times x, 6x. 8 plus 18 is 26 times 8 is 28, right? So I need to subtract 36 from both sides. That gives me 6x equals 70, 82. Is it 172? Okay, thank you. Divide both sides by 6. And x equals 2 times with 12, 52. What is it, 20? Isn't it? It's going to be 0.6 repeating, isn't it? So we don't solve a variable for repeating decimal ever. This is the same thing as saying 28 and 2/3. Yeah. How do we feel about that? Goodly? Not really? Nathan, you shook your head like, meh. Yes. Huh? Getting it? Okay. Ow, ow. All right. So this one, think about ow, ow. This is the same thing. Ow, ow. You're still going to use ow, ow. So you either, this is why this is so easy. You either multiply the pieces that create each segment or you just use ow, ow. That's really how it works. So I'm going to draw ow, ow for you first. So this is the outside times the whole segment. This is the outside times the whole segment. What do you notice about segment TR? It's the same thing. So it's just O squared, sure. But I'm still going to write it as ow, ow. Okay. So it says if a tangent segment and a secant segment are drawn to a circle from an external point, then the square of the measure of the tangent is equal to the product of the measures of the secant segment and its external segment. So let's write out what this looks like using the segment names. So segment TR, segment TR, the quantity squared equals the outside WR times the whole segment RS. Still an out. You just have to think about what out means. Are we okay with that? Okay, so let's take a look at this. I scanned this, and it is such a bad scan that, I mean, it's not a great copy in the first place, but the scan really just didn't do it justice. Okay, so this is an out, right? Out equals out. Outside, 10 times the whole segment, 10 equals the outside, 6 times the whole segment, which is, good job. So let's see, 10 times 10 is 100 equals 36 plus 6x. When I subtract 36 from both sides, 64 equals 6x. Divide both sides by 6. 32 thirds equals x, which is the same thing as 10 and 2 thirds. How do y'all feel about that? Great. Okay, I'm going to freeze that for a second.